A wind turbine blade weighs several tons and spins continuously through rain, salt air, and temperature extremes for decades. A car engine crankshaft completes thousands of revolutions every minute under enormous load. A dental drill spins fast enough that air resistance is a design consideration. All of these should grind themselves apart. Metal pressing against metal under load generates heat. Heat accelerates wear. Wear creates failure. The physics suggests none of these machines should last more than minutes. Inside each of them, hidden from view, is a ring of small polished steel balls sitting between two metal rings. That arrangement changes everything. How can something so small carry so much load for so long? The answer involves a physics insight that is almost obvious once you see it, and a manufacturing process more precise than almost anything else in industrial production. Let's get into it right here on Small Things. Rolling instead of sliding. At its core, a ball bearing replaces sliding friction with rolling friction by placing hardened steel balls between a rotating inner ring and a stationary outer ring. The inner ring attaches to the rotating shaft. The outer ring sits in the surrounding housing. The balls roll in shaped grooves called raceways. A cage holds the balls evenly spaced. A film of grease or oil fills the space between the surfaces. The shaft and its housing never touch each other directly. The load passes through the balls. The balls roll rather than slide. Friction drops to a fraction of what sliding contact would produce, and a bearing built correctly can outlast the machine around it. A principle that waited for the bicycle. It did not begin with industry. It began with the observation that rolling is far easier than sliding. Ancient builders moved heavy stone on wooden logs rather than dragging them across bare ground. Roman engineers launched ships on timber rollers rather than pushing them along their keels. Medieval millwrights placed round stone beneath rotating shafts to reduce the grinding friction of plain bearings. The principle was understood intuitively for thousands of years before it could be measured with instruments, manufactured with consistency or scale to meet the demands of industrial machinery. Rolling reduced effort. Every craftsman and engineer who built something heavy understood this from direct experience, even without the ability to explain precisely why. The modern ball bearing took its recognizable form through the bicycle industry in the late 19th century. Designers building lightweight high-speed bicycles needed wheels that could spin freely under load without the axle grinding against the hub. Filling the hub with a small hardened steel balls sitting in circular grooves solved the problem immediately and measurably. The wheel ran on rolling balls rather than sliding surfaces, and the improvement in smoothness, efficiency, and longevity was significant enough that engineers from other industries noticed quickly and adopted the principle for their own applications. The design spread into every class of machinery. Electric motors, machine tools, pumps, and railway equipment adopted bearings through the early 20th century. Standardization of bearing dimensions was critical to how quickly the adoption spread. A bearing from one manufacturer that could fit any housing built to the same specification created an interchangeable industrial system that still underpins manufacturing worldwide. A standard bearing purchased today will fit into any housing machine to the same dimensional standard everywhere, regardless of which factory made either component. Precision increased in step with the industry that bearing served. Early bicycle bearings were made largely by hand and varied considerably from piece to piece. As machine tools and measurement techniques improved through the 20th century, tolerances tightened until the roundness of a production ball became measurable in millions of a meter. Jet engines, gyroscope, and computer hard drives pushed that precision higher with each decade and continue to do so. The same basic component concept from a Victorian bicycle hub is now inside spacecraft attitude control system and commercial aircraft turbines. The physics has not changed. The precision with which it is applied has changed entirely. why the ball has to be nearly perfect. So how do a few steel balls prevent metal from destroying itself under continuous load? The key is the fundamental difference between sliding and rolling. When two metal surfaces slide against each other under load, friction generates heat at every point of contact. The harder the press and the faster the motion, the more destructive that heat becomes. Plain bearings, solid cylinders of metal, rotating inside a housing. They need constant lubrication and steel wear progressively despite it. When the same load is carried on rolling balls, each ball contacts its groove at a geometrically tiny area. The ball rotates through the grooves rather than dragging across it, because the contact point is rotating, not sliding along the surface. So friction falls to a fraction of what sliding would produce. The physics of rolling generates far less heat than the physics of sliding. But this only works when the balls are nearly perfect. A ball that is slightly out of round creates a shock load every time the imperfect area cycles through the load zone. Surface roughness gouges the raceway rather than rolling cleanly to it. A ball fractionally larger than its neighbor carries more than its share of the total loads and wears faster. Bearing balls begin as wire of high-carbon chromium steel cut into small slugs. Each slug is compressed in a die to produce a rough sphere. The seam is removed and the ball enters a series of grinding and lapping stages that progressively refine its shape. A finished production ball is typically round to within half a micron, roughly 1/10 of the width of human hair. Its surface is polished to a smoothness approaching a mirror finish. The raceway the ball run in require the same standard. They are ground with diamond tool, then polished. Heat treatment hardened the steel so the raceway surface can withstand the concentrated contact stress of loaded rolling ball without deforming over time. A deformed raceway changes the geometry and the bearing stops working correctly. Hardness is not the explanation. The most common assumption about bearings is that their strain is what matters, that hard steel simply resists the forces involved by being robust enough. Hardness is necessary, but it's not the explanation. A bearing of hard steel with poor dimensional accuracy fails quickly. If the balls are not exactly the same size, the load does not distribute evenly. Some balls carry more than their share and wear faster. If the raceway are not precisely shaped, the balls cannot roll cleanly. If the balls are not round, every rotation produces a small shock as the imperfect geometry cycles through the load zone. Vibration builds, heat builds. The bearing fails well before its material strain would suggest it should. Lubrication is more specific than it appears. At the contact between a rolling ball and its raceway, despite the small area, the pressure is high. Under that pressure, lubricants forms a complete separating films. The ball rides on the film rather than directly on the steel. The chemistry of the lubricant, its viscosity, its operating temperature, and its ability to clean the material surface all determine whether the film forms and holds. Wrong lubricant or wrong quantity is one of the most frequent causes of bearing failure in service. Different applications are genuinely different engineering problems. Hard drive bearings spin under almost no load at high speed. Wind turbine bearing turn slowly, but carry forces measured in tons. The right bearing for one application would fail quickly in another. From dental drills to wind turbines. Today, you will find ball bearings in essentially every machine that rotates or moves under sustained load. The smallest production bearings are used in dental drills and miniature motors with outer diameter of a few millimeters, while the largest support wind turbine nacelles and mining excavator pivots, with the diameters exceeding several meters and individual weight of several tons. Between those extremes sits a continuous range of types and sizes, each chosen for a specific combination of speed, load, temperature, and environment. In electric vehicles, bearing friction directly affects efficiency. A bearing running with a slightly higher friction than its design specification consumes electrical energy continuously over the vehicle's life. The difference between a correctly specified bearing and a marginally worse one is measurable in driving range. In aerospace, engine bearings must survive temperatures that destroy standard lubricants at rotational speeds that would fail ordinary steel balls. Silicon nitride ceramic balls replace steel in these applications because they are lighter, harder, and retain their properties at higher temperature. The component looks similar to a standard bearing. The material and tolerance are entirely different. Every finished bearing is inspected for dimensional accuracy, surface finish, noise, and vibration before leaving the factory. A bearing that passes is rated for a calculated service life under defined loads. A bearing that fails any check is reworked or discarded. The standard is not set by what most bearings can achieve, but by what the application requires them to survive. Turning friction into rolling motion. So how do small steel balls allow a heavy machine to move smoothly? By replacing sliding with rolling. By distribute load across multiple contact points that cycles through the load zone continuously, sharing the burden across the whole bearing rather than concentrating it at one place. By being made with a precision. That means the geometry of every ball, every groove, every spacing element works together to keep rotation clean and controlled for years of continuous operation. Heavy machines do not move smoothly just because they are powerful. They move smoothly because tiny and precisely made steel balls quietly turn destructive friction into controlled rolling motion. Hidden inside every rotating machine is this small, exact component, doing one of the most important things in engineering without making a sound. If this video changed the way you think about the machines moving quietly around you, let us know in the comments what you want us to look at next. We might make it in our next episode. Thanks for watching. History often hides in the smallest details.